Now we've covered everything in Chapter 7, so let's kind of put it all together and review what we've learned. We learned that a number that describes the whole population is known as a parameter. That is a fixed number that is a single number that is true for the population. It might be a mean, it might be a proportion, but it is a specific number that describes the whole population. A number that's calculated from a sample is known as a statistic. Now, depending on what particular sample that you get when you randomly sample from a population, the statistics can vary. You could get different sample means, different sample proportions based on different samples. We always use a statistic to estimate a parameter. The two we've looked at is that in section 7.2 we used a sample proportion to estimate a population proportion, and in 7.3 we used a sample mean to estimate a population mean. So let's look at the sampling distributions for each of those. So we're going to look at the sampling distribution for sample means and the sampling distribution for sample proportions. So let's just start with the symbols that we use. So the parameter, which deals with, of course, with the population, we call P, and the statistic we call P hat. There are some books I've seen that use pi instead of P for the population parameter. So if you see that might crop up in a problem somewhere. The parameter for means is mu, and the statistic is x bar. So mu and p are fixed numbers, they don't vary, but p hat and x bar can vary. So when we take lots and lots of samples of the same size, in fact all possible samples of the same size from the same population, and we compute the statistics from all those possible samples, then we get what's called a sampling distribution. So we have the sampling distribution for p hat, which has all the possible sample proportions from all possible samples from a population of categorical data. So if we have a categorical data, we're looking for data that falls in categories. It's not something you can take an average of, but you could find the proportion in that category. So our example that we started with in class was the Reese's Pieces example. Reese's Pieces have different colors, orange and yellow and brown, I think. And so we would have, our population would look like 3 bars, one for orange, one for yellow, one for brown. And we would have these categories, and the population, or the proportion of orange in the whole population would be P. The proportion of orange in my sample would be P hat. But if you took a sample, and each member of the class took a random sample, we'd all get different P hats. And if we found all possible P hats and arranged them in a distribution on a scale, like this might be 0.4, 0.5, 0.6, 0.3, 0.2, and so forth, and we arranged how many of each value of P hat we got, we would get a distribution that looks approximately normal as long as our conditions are satisfied. Same thing here. This is a quantitative variable. I didn't write that down, but this would be a quantitative variable, something you can find the average of. So if I were to take a sample of data and find the average value, we used heights in class as an example. We found the average height of a sample of class members, and we plotted a bunch of different x bars, and we found that they made a distribution. Now if we could get all possible samples of the same size and get the sample means from all of those possible samples and put them in a distribution just shows what values they can take and how many of each value. We could see that we would have some sample means that are higher than the population mean and some sample means that are lower than the population mean, but all together they would form a distribution that's centered at the population mean. This means that P hat is an unbiased estimator for P because all of the sample P hats have an average of P, and a sample mean is an unbiased estimator for mu because all the sample means cluster around the true population mean, which is their center. Let's look at the different characteristics of these sampling distributions. First of all, what is the shape of the sampling distribution? we know the sampling distribution will be approximately normal if we verify what's called the large counts condition. That's not supposed to be plural, the large counts condition. There we go. So for proportions, we have to verify that n, the sample size, times p, the population parameter, population proportion, is greater than or equal to 10. Or n times 1 minus p is also, and I should say n times 1 minus p is also greater than or equal to 10. So as long as that condition is satisfied, the distribution of sample proportions will be approximately normal. If n is greater than or equal to 30, or if the population is already approximately normal, then it doesn't matter what my sample size is, the distribution of sample means will be approximately normal. Now this n is greater than or equal to 30 is a rule of thumb based on the central limit theorem, which says if my sample is large enough, no matter what the original population looks like, no matter what its shape, the distribution of sample means will be approximately normal. What about the mean of our sampling distribution? Well, we know the mean of all of my sample proportions, all of my p hats, will equal the population proportion. And the mean of all of my sample means will equal the population mean, as long as I've taken random samples in order to obtain those p hats or those x bars. If the p hat or the x bar comes from a simple random sample, then this condition is satisfied. What about the standard deviation? The standard deviation of my sampling distribution for p hat is this formula right here, the square root of p times 1 minus p over n, where p is the population proportion and n is the sample size. For my distribution of sample means, sigma of all my sample means, the standard deviation of all my sample means is the standard deviation of the population divided by the square root of the sample size. Once again, there's a condition that allows me to use these formulas, and that is called the 10% condition. I have to verify that as I'm sampling without replacement from a population, that the sample size is small enough that those probability of getting each of the different individuals from the sample won't change, or from the population won't change very much. So I have to verify that the sample is less than 10% of the population, which can be symbolized little n is less than or equal to 0.1 times big N. Now, what if I wanted to find the z-score for the normal model for my sampling distribution? Remember that z is x, the individual data value that I'm looking for, minus mu divided by sigma. And z tells me how many standard deviations x is from sigma. X is from the mean, mu. So when I'm talking about the distribution of sample mean or sample proportions, my individuals in my distribution aren't values of x, they're values of p hat. And my mean isn't mu, it's p. So I take the difference between p hat and the center of the distribution, which is p, and divide it by the standard deviation of p hat. When I'm looking at a distribution of sample means, all the individuals in my distribution are all x bars, or all sample means. The center is mu, which is the population mean. So I have to do x bar minus mu divided by the standard deviation of x bar to see how far away all of my particular x bar is from mu. Now, looking at how this works out in a probability distribution, the mean would be my parameter, either mu or p. The statistic would be from a sample, either p hat or x bar. So I'm trying to figure out how far away the statistic is from the mean. How well does the statistic estimate the mean? The probability here, the area under the curve, is the probability of getting this statistic or something farther to the right if all of my given information is true. The z-score just tells me how many standard deviations between the mean, which is the parameter, and the statistic. So that's how you would calculate the z-score for each of these sampling distributions. Now the only other thing to point out was just remembering our binomial distribution This is not in Chapter 6. It's not being tested in Chapter 6. However, often problems that involve proportions could also be done using the binomial model. So how are they different? In this case, we're looking at basically the distribution of x. I'm going to put a little x in here. So we're saying mu of x and sigma of x. In other words, if x is a discrete random variable, what is the, based on categorical data, we're saying how many x are in a particular category. So the expected number would be the sample size times the probability of getting that x value. And the standard deviation is the square root of NPQ. So it's the distribution of how many, in other words, x. Now if I want the distribution of what proportion, then I'm looking at a distribution of p hat, and p hat is x divided by n. So mu of p hat is np divided by n, and sigma of p hat is the square root of npq divided by n, which simplifies to this p for mean and this standard deviation for p hat. The other important thing to remember about this unit is the central limit theorem. Make sure that you go in and actually write down the definition of the central limit theorem, because that is an extremely important thing to know as well. Now, the other thing I passed out in class today was the key to 7.3 number 53 and 7.3 number 55, and I did that for two reasons. One was to show you what proper work looks like in this unit, and the other was to just emphasize a couple of key concepts. So first of all, this was the given information in the problem, and I just wrote it down kind of to summarize here. This is the population, mean, and standard deviation of the distribution of blood cholesterol levels for individual men. Okay, so this would be, all of these x values would be for blood cholesterol levels for individual men in the population. A sampling distribution of x bar, where x bar represents the mean blood cholesterol level of 100 men, would be slightly different. You were asked to describe the sampling distribution. When you describe a distribution, you have to say, what is its center, what is its spread, what is its shape. If it had outliers, you would also describe that, but sampling distributions don't have outliers. So we're thinking of that SOCS, S-O-C-S, shape, outliers, center, spread. So these are all tied to certain conditions. So you need to state the condition and then show the characteristic of the model that goes with that condition. So if we have a simple random sample from the population, those sample means will have a mean that is equal to the population mean, which is 188. If the sample size is less than 10% of the entire population, then the standard deviation will have this formula. It gives our standard deviation. If the sample size is greater than 30, or if the original population is approximately normal for means, the central limit theorem says that the distribution of x bar is approximately normal. So these three characteristics describe the distribution of sample mean blood cholesterol levels for 100 men in the sample. Now, the next one says, if I am using this 100 men sample, what's the probability that that sample will give me a mean value that is within 3 milligrams per deciliter of the population mean of 188? So in other words, what's the likelihood that I get between 185 and 191 for the cholesterol level with a sample size 100? So I have to use this previous model, use that mean and standard deviation, use my normal CDF, calculate that. I just want to remind you that the normal model drawing is always considered correct work. You have a shaded area, you have your boundary lines, you have your mean and standard deviation. That is always going to give you full credit for work. The normal CDF with the numbers labeled might give you full credit. I did see one instance on the NAP exam where they didn't get full credit for that, But if you just write normal CDF with no labels at all, you certainly won't get any credit. So I really want you to draw the normal model sketch. So this is the answer. There's about a 53.57% probability that X bar estimates mu within plus or minus 3, in this case it was milligrams per deciliter, of the true mean. Now the next question asks, if n is 1,000, how does that change? Well, the big idea here is with the larger sample, we get a smaller standard deviation. Therefore, the percentage of data that's close to the center increases. So we are more likely to get a sample that estimates mu within 3 units, plus or minus 3 units, with a larger sample than we would with a smaller sample. Now on the next page, the big idea is the comparison between a normal model calculation with the population distribution and a normal model calculation with the distribution of sample means. So the population distribution of fill amounts of a bottle of cola has this mean and this standard deviation. The probability of randomly selecting a bottle of cola that has a fill amount of less than 295 milliliters can be calculated using this normal CDF here. Now, if I took a random sample of 6 bottles and I wanted to know what's the probability that the average fill amount in that sample of 6 is less than 295, I would have to create a distribution of sample means. So I'd need to check, do I have a random sample? Is 6 less than 10% of all cola bottles? Is the population of cola amounts approximately normal? Or sorry, is the sampling distribution approximately normal? Well, the population is approximately normal, so even though I have a very small sample of bottles, the distribution of X bar is still approximately normal. But when I do the calculation now, since I've divided the original standard deviation of the population by the square root of 6, I have a smaller standard deviation. Therefore, there's most of the X bars are closer to 298 than the individual bottles would be. So it's a smaller proportion that would be less than 295. So the big idea here is that the fill amounts in individual bottles will always vary more from the mean, will vary more, I should say, than the mean fill amount in a random sample of bottles. So it's more unusual to find X bar less than 295 than X less than 295.